don't like. Those who don't like, of course, say academia should be independent of the result. I don't want to waste your time with that discussion. So at some point 5 years ago, there was a company in Vancouver. It was named 3V Geomatics. And what they did was that they processed satellite images. So they had the satellites, which was taking pictures of the world, and they would take those pictures, those images, and they would process it. For example, if there was an American company building a big building in Dubai, and they wanted to know how the building is progressing, they would hire 3V Geomatics. 3V Geomatics would take the pictures from the satellite, would process it, and would tell the American company that, things are going well. So the problem they had was that the images, when you have satellite images, sometimes it's cloudy and the quality of the image is not good. And you see that problem in many, many different places where you have an image which the quality is not good. And of course, like think of old family pictures that you find in an album, and the color is gone and it's probably not very straight, twinkled. So you want to improve the image, right? That was their problem. And they asked us, can you help us? So then we started looking at different solutions. How do you improve an image quality? So we looked at old solutions, conventional solutions, mathematical solutions, and we then also looked at modern solutions, like artificial intelligence solutions. So we looked at algorithm. When I talk about algorithm, I really talk about mathematics and functions and typical solutions that existed from the past. And when I talk about data, I'm really talking about newer solutions which rely on data, and in essence, machine learning. So that's how we got into this problem. We had bad quality images. We want to improve the image quality. There are two classes of solutions: old conventional solutions, which we call algorithms, and then modern database solutions. And that problem, improving images quality, is called the super resolution problem. And I'll tell you a bit more about this. So the problem is super resolution. There are two classes of solutions. We want to see which is the better one. So that's the basic idea that I want to talk about, and would be taking your time. So next slide, please. Okay. So often when I teach my classes or give a presentation, I start with one slide and I tell the audience that if you want to remember one slide from this entire presentation, this is the one. So if you just listen to me for 1 minute, you'll leave this room with some idea. So as I said, in summary, here's what we do. We try to investigate machine learning solutions to math solutions. That's the idea. We refer to machine learning solutions as data solutions, math as algorithmic solutions. And the case study here is an image quality enhancement. And the key result here, if you look at that table below, you see it has 3 columns. The first column is like two metrics. One is error, one is similarity. And I tell you what they are. Obviously, error means, how bad we're doing, and similarity is like how good we're doing. And then you see the second column, machine learning, gives you 2 numbers. And the third column, algorithm, gives you 2 numbers. So when we look at error, the machine learning is 0.95 hundredths of a percent. Algorithms or math solutions give us 1%. So it's pretty competitive. And when we look at similarity, and I'll tell you later what similarity is, basically how similar is this picture to that ideal picture, then you see the numbers 89% and 86%. So the numbers don't matter that much. All I want you to remember from these numbers is that they're very close. So we have a very competitive solution. Just remember that. The rest is nothing. So again, we have a problem, 2 different solutions. We test it, and then here is the number. And at the end, the numbers are very close. I'll come back to this. So basically, we're dealing with the problem of image interpolation. So on the left side, You see it, think of an image, think of those dots as pixels. You have a function, you only have a few points of it, right? In this case, 6. And you want to find out the curve to the right. So the question is, how do you build, how do you produce, how do you find all those missing points? That is what we call image interpolation. So here's it comes down to this. You have some points, you want to see how you connect them. What is the missing information? How can you generate that information? So remember, we need images. So why do we need image interpolation? We need, if sometimes we have a small image, you want to go to a bigger one. If sometimes we have bad quality image, we want a good one. Sometimes images is just not attractive. We want to make them cool. So interpolation algorithms, I just list 5 of them here to the right. You have nearest neighbor, linear, cubic, bilinear, bicubic. 5 of them. I'll just quickly go over, but I want to say right away that the best of them is the bicubic, and you see why. So nearest neighbor is pretty straightforward. In this algorithm, it's a very basic method. It requires the least processing time. Now, that's an important. I want to draw your attention to an important piece, and I'll come back to this later. In this day and age, where you have computers and computers are consuming power, one of the things that we really care about is to make sure computations are low, because lower computations means that things will happen faster, and you'll get the results faster. So nearest neighbor is pretty straightforward. It's a piecewise constant function. And in essence, it makes the effect of, it makes each pixel much bigger. So if you have like 4 pixels, this is like colors. Like imagine, you want to go from the small 4 square one to the bigger one. All you do is that you look at the missing points and you just see which is closer to which color, and you pick that. So as you can see, then you have one corner is all red, one corner all blue, one all green, and one white and one black. So all you do is that you look at neighborhoods. This is a very basic element. Then what else do we have? Okay, you have to help me with this. And then, so this is how the algorithm would look like. This is function fx, this is x. As you see, every point, these are the dots that we have, right? And then whoever is close to this dot will get the same value. When you pass this stage, now you'll get closer to this dot, then of course you pick this one. So on and so forth, and this is how you have your system. There are other interpolation algorithms. For example, this is the linear interpolation 1D first order. As you see, again, you have your dots, and all you do, you connect them with lines. Pretty straightforward. You have a function, a linear function representing these lines, a1x1 plus a0x0. You have 2 points, 2 unknown variables. It's easy to solve, right? Again, pretty easy. But as you can see, this is it's a linear approximation. Then you can have what we call cubic. Now you're trying to model this using a cubic equation, a3x3, a2x2, a1x1, a0. Of course, now you have 4 variables, a0, a1, a2, a3, and you would need 4 points to solve the problem, right? Again, so just an interpolation solution. Don't worry about the details. The idea is that, again, you have a piecewise cubic function. It helps you find these missing points. Then we have bilinear. Now in bilinear, there's an equation. I don't want to take your time with equations. You see the equations. Then you have, like, for example, 4. This is the 4 points that you have. Again, first of all, note that you have 4 unknown variables: a0, 0, a0, 1, a1, 0, a1, 1. Then you have these 4 points. What you do basically is that you generate this point, interpolate. You use this and this, build this one. You use this and this, build this one, and then you use these 2 to get this one. So and then you find you solve the problem. You find the variables. Again, these are all mathematical solutions. Moving on. Now this is the one that I want to talk about a bit more. Bicubic interpolation. This is the best interpolation solution. What it does is that if you have 2 points and you want to find the point between the two, you not only look at point 1 and point 2, you also look at the slopes there, derivatives, right? So that's an interest because you also consider the slope, and that helps. And that's why this in the bicubic method produces the best results in conventional solutions. Again, so here's, you use, now you have these curves because, of course, you are looking at slopes. This is how it would look like. These are the equations. So in essence, what I want you to remember until this minute is that we have 4 or 5 different mathematical models to do image interpolation, right? That's all I want you to know so far. And this was the first class of solution. And to produce some result, this is some images, right? So the one on the left is the nearest method, the one which is the most simple, very easy to implement. Then you see bilinear. And at the right side, you see bicubic. You can see that bicubic is significantly better than the nearest, right? You can even see it, but then you may ask me, really, is bicubic better than bilinear? I can't see that. I would argue it is. If you just pay attention, to some corners of this image, but again, what I want you to remember, bicubic, best method. Let's move on. And this is another example. On to the left is the original. Then you have the 3 methods. And as you can see, bicubic is the closest to the original picture here. That's all. Well, now let's look at the second class of solutions, which is machine learning. So what is machine learning, basically? Basically, it's some method which relies on automated learning. It gets computer to work for you. And the tough part is writing the software, but the data would do the job. So how does machine learning work? Excuse me. So how do you, first of all, machine learning neural networks is really made after our brains. How do you know your friends? How do you recognize your friends? You see your friends the first time, your brain records the image. Maybe if you see this in the second time and it has been a while, you don't recognize them and you say, oh, sorry, where did I see you before? But then your friends say, oh, we met here and there, we met in Samarkand. And say, oh, okay, then your brain starts to learn, right? So that's machine learning is the same idea. You keep giving it data and it would learn what data is. So in essence, if we want to teach a machine to know what an apple is, we give it 1,000 pictures of an apple and we say, listen, apple, 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 apple. And it would, okay, then at some point it would understand or learn what an apple is. Then when you give it apple 1001, it will says, okay, I've seen 1,000 apples before. I know what an apple is. That's why we call these data solutions. You could have told the machine that, listen, I'm going to give you an algorithm. There is this thing. It is in a circle. It's round. It is red or green. It is if it grows on trees. And you can give some steps and then, okay, this would be then apple. This is not like that. You just give it enough number of apples and it would realize what an apple is. So that's why we call this as automating learning, because the computer does the job. All you have to do is to give it enough data. So another way to look at it is that in traditional programming, you have a computer, you give it data, you give it program, it produces the output. In machine learning, you give it the data and you give it the output. You give it the input and output, and then the machine produces the program, right? The machine builds the solution. You only give it the data for what input, what output you want to see. So in essence, it's like a magic. Conventional solutions were like gardening. But how is it here? So here, as an example, in this kind of solution, the seeds are algorithms, the nutrition is data, the gardener is you, the plants are programs. So you give it the data and then program grows. All you have to do is to produce the data. So what we did later on, our machine learning solution, was that we were trying to improve images, and we had low resolution images, and we wanted to find high quality images. So here's a problem. I want to spend a couple of minutes telling you what's interesting. Why? If Improving images, there's one way to do it. Like if I have 1,000 bad quality images and I have 1,000 good quality images, same images, but good quality. I mean, 1,000 I'm using as a number, it's really millions. And I give it to the machine and say, listen, this is a bad picture of Amirali, bad quality, and this is a good picture of him. And then I give that 1,000 times. The machine will learn, right? So then when I bring image or picture 1001 and it's bad quality, the machine says, yeah, okay, I know how to fix this, I fix it. Here is the problem. A lot of times you do not have any good quality images. Like you go to your grandfather's closet, you see there are some old bad quality images, you bring them out and they say, oh, I want to improve them. Oh, let's use machine learning. Okay, so where are the good quality images that I can use to teach? There are not any good quality images. All you have is bad quality images. So then in that situation, how are you going to teach the machine? The machine needs to see good quality, bad quality, look at them, then learn. You have a situation where all you have is bad quality. And that is true with satellite images, because satellite images, if they're bad, they're bad. There is no ground truth. There is no perfect picture that you can compare. So what we did, and this was the creative solution that we used, was that we said, okay, you have some bad images. I am going to make the bad images even worse. You see what I did? We got the very bad, the bad images, and we even made them worse, much worse. So now we had 1,000 pictures which were bad, and 1,000 pictures which were very bad. Then we were able to train the machine to go from very bad to bad, right? So now the machine knows how to go from very bad to bad. Then we said, aha, now we're going to give the bad images to the machine as input. And then the machine will give us good, because the machine has learned to improve images. That's what we call super resolution. Super resolution means producing good data when even you don't have the methods to, when you don't have enough information to train. So the challenge, as I said, was we had high resolution images were not available. We were not able to train. So we decreased what we did. We decreased the resolution of images. We used them as low resolution samples, very bad quality. Then we used the original images as medium, like, just bad quality. And then we provided the machine learning with these two groups. And then what happened was this. So what I'm showing you here is, as you can see there, you see three pictures, right? The first, the middle one was the mid-resolution images. This is what we did have available. We wanted to produce this. We only had this. So what we did, we reduced the quality. We made some low resolution images. Reducing the quality is always possible. We trained the machine and it learned how to go from low quality to medium quality because we had the information. Then here was the magic. We used the same machine, but this time, instead of as the input, we gave it the medium resolution images, and it gave us the high quality images that we like. So in essence, we produced information. And I think that's a very interesting phenomenon to think about. There is information which is not there, we were able to produce it. And I can talk more about this if you like after, but I think that's a very promising situation. So then let me take you back to what we're trying to do. Let's do a recap. We have a problem, image improving, two solutions. One is conventional, one is modern. We're trying to experiment. So we need to do some experiments. So a neural network, which is very popular, is called CNN. Has nothing to do with the news TV channel. This is convolutional neural networks. It just has the same abbreviation. And so we tried these networks, CNN residual networks. So what is a neural network? Many of you know, it's basically some inputs connected to some outputs. You train, the weights are decided, and it's built after a brain, a human brain. I don't want to go into this. What you want to remember is that you do some mathematics. and you decide how these inputs reach the output, what are they multiplied, and how this works. CNN convolutional neural network is basically a neural network. It has convolutional layers. So convolution, you know what it is, but in this context, you have a matrix of number, and then you have a second matrix, and you just move it around and multiply the corresponding numbers. It gives you some data. Now, some of you might have heard the word deep learning. Deep learning means that you have a convolutional network, and instead of having one layer, it has multiple layers. Again, don't worry about the mathematics. I know this might be too much for some of you. All you need to remember is that information arrives, goes through many, many steps before it produces the outputs. All that's important. So when we wanted to evaluate this, we have two terms. One is error, RMSAE. This is the mathematical formula. Again, don't worry about it. What it's showing is that if you have a perfect solution and if you have an imperfect solution, how do you compare them? What is the distance between them? This number, if it's higher, it means your system is worse. If it's lower, it means your system is better, right? Because it's error. So the lower RMSE, the better. Now but we had a second metric, which is SSIM, structural similarity. It's just another mathematical measurement. It shows how similar, like, if this picture is to the other picture. Now here it is similarity so the higher the number, that means you're in better shape. Now look at this chart. So I said all this to show you something like this. What I'm showing you here is that on the left side in green, you're seeing error, right? You see two bars. Under bar 1 says CNN, under bar 2 it says bicubic. As you can see, bicubic, which was the mathematical old solution, is giving you less error, right? So this one says, oh, bicubic is better. You spend all your time on this modern machine learning, and guess what? You got worse results. Bicubic wins. If you look at the right one, it is similarity. Similarity is the other way. The higher it is, the better the system. Now here suddenly you see CNN is winning. It's higher. So you're like, oh, wait a minute, who won? One referee says old methods are good. The other referee says new methods are good. We don't know. It's a tie. Let's move on. By the way, this is a picture I'm showing you. On the left is the perfect solution. Middle is the machine learning solution. Right is bicubic. You see, the middle one seems better, even though the error was a bit higher. There's another network. I'm going to go through this a bit faster. So some people have improved CNNs. What they do is that in a typical CNN, you have layers connected like this. Layer 1 sends the output to layer 2. In residual network, you not only do this, but you also have this bypass stage that the input directly goes to the output as well. Why they do that, don't worry about it. Their studies show that this works sometimes. So we said maybe CNN was a bit behind sometimes. Maybe if we go to a better solution, residual networks, that works better. And then guess what? Here is the result for residual network. On the left, you see error. ResNet is our solution. It produces lower number compared to bicubic, so it's better. On the right, you see SSIM, and again, ResNet produces better results. So remember I said it was a tie before? CNN was like bicubic. Now you see, no, like the modern system is obviously winning. And this is the picture. On the left, ground truth, modern solution in the middle, bicubic on the right, and as you see, the image is well known. You can see that the neural network, the database solution, is the winner. So in summary, what did I tell you? We started with a question that who is better, data-based solutions or algorithms? We all went over them. We looked at 5 different conventional methods: nearest neighbor, linear, cubic, bilinear, bicubic. Bicubic was the best one. So we picked that one as the winner of that group. Then we looked at machine learning solutions, deep CNN residual. There was another one, GAN, I didn't go over. And then we realized that, this residual network works best. So I would stop here, but I want to say one more thing. The difference between the two methods is not that much. It's very little. Maybe if we're talking about 1% difference, maybe if I found a different set of images, this would be different. So what I want you to take away, I mean, you hear machine learning, you hear deep learning, you hear artificial intelligence. What the lesson here is that still many of our old methods work very well. And one should not be fooled by the hype, by the propaganda, right? If the jury is out. You have to think about that. You have to look at the application. Sometimes machine learning works for you, sometimes it does not. And it's really the scientist, the researcher, the honest researcher who has to pay careful attention to these details before they decide who wins. Thank you very much, everybody, for your time, and I hope you have liked it.
Thank you very much for very interesting talk. Please, any questions? Yes, please.
Is a modern example of Ilpo's problem, as you know. In this case, two very similar objects or data about these objects, two sets of data about this object may give, after reconstruction by algorithms or by machine learning, may give two different solutions. Have you examples in your works about such examples about the construction by algorithm and by machine learning? And what kinds of decisions, these problems you suggested?
So if I understand the question correctly, if an apple is like very much looks like an orange, the system may make a mistake, right? That's your question. Yeah, so that's why we report error. So in machine learning, the way the things that you have a set of data sets available to you, right? And when you look at errors, we are testing like, I don't know, 500 million images. So we never have the chance to look at, individual images. We run the whole thing, we compare the results, and we get some number. So when you see like accuracy here is 88%, that means 12% of the time we weren't able to predict or make the right prediction. For some data sets, if they're simple and there are mathematical explanations, your error could be very low. For some data sets, the error is very high. We have had cases of like 50% error. So that's that. Yeah, I hope I answered your question. There was another question.
Yeah, any question, please?
I have simple question. So let's say we have some picture, but it doesn't have some part of the picture, doesn't it?
Sorry, what was the question?
Some picture is the part of picture missing.
Yes.
Is it possible to improve this picture to the original picture? Have you understood me, please?
So your question, if the part of the picture is missing, can we generate it?
Can we improve? Yeah.
Yes.
Can we reconstruct?
Yeah. So
thank you.
yes. So obviously, the big part of the picture, no. But if you have, so let me put it this way. So let's say you have a picture of a hand. And in this picture, I don't know, one small part of the hand is missing. So what we do is that we may, of course, if you have a perfect picture of the hand, you can find it because it would compare real life. Now, if you don't have the perfect picture of the hand, we take the picture of the bad picture, and pick another spot of it out. Now the system, because it learns that, oh, I fixed this one by, making the finger, I don't know, 1 centimeter longer, again, it would do it again. And then, sometimes with like algorithms like that, you add pieces which weren't there, but it's not always the case, but sometimes depending on the nature of the image, yes, we have seen that. Yes, thank you.
Okay, any more questions? Okay, let's thank speaker.